Hi, last month I reviewed an OWON HDS120 handheld oscilloscope and multimeter combo device, and many of you had commented that you'd like me to do a review on an HDS160, and that is what I have here today on Workbench. Thank you, Banggood, for sending me this unit. As usual, I will leave a link in the video description below for those who are interested in getting one after watching this video. So first thing first, what are the differences between the HDS160 and the HDS120 that I had reviewed before? Well, the spec sheet that comes with the HDS160 actually has the specs for both these models side by side, which is kind of convenient. So let's actually take a look. As you may have spotted already, the main difference between these two models is the multimeter counts. For the HDS120, it has 20,000 counts. As you can see here, the maximum number is 20,000. Whereas for the HDS160, you can see that the counts is 60,000 here. Also, if you look carefully, the accuracy in different ranges are actually quite comparable between these two models. In some ranges, the HDS160 actually is slightly better. For example, in the DC current range, you can see that the accuracy is actually at 0.15% versus the 0.8 or 1.5%, depends on the ranges on the HDS120. So when everything else stays equal, having a higher counts meter is obviously preferable, as it can give you higher display resolution without having to switch to a higher range. I made an entire video explaining multimeter counts and digits, and I would recommend you check it out if you are interested. I will include the link to the video in the cards above. Anyway, let's go back to the specs for a moment. As an example, you can see the lowest DC range on the HDS160 is 60 millivolts, and the lowest DC voltage range on the HDS120 is 20 millivolts. This lowest range has a 1 microvolt resolution on either of these meters, and that is the case if you are measuring the voltages under 20 millivolts. Both of these meters will give you the same voltage resolution. But if, say, you are measuring a 50 millivolts voltage, the HDS120 can't do it in the 20 millivolts range, so you'll have to switch to the 200 millivolt range. And in this range, you see that the resolution changes to 10 microvolts instead of the 1 microvolts. But on the HDS160, you can measure it within the 60 millivolts range, therefore you still have that 1 microvolt resolution. So clearly, this case illustrates one of the many benefits of the higher counts HDS160 brings. And if I flip it over, you can see that the HDS160 can also measure higher capacitance up to 60 millifarads and higher frequencies up to 60 megahertz. And this is directly related to the higher counts. On the HDS120, the capacitance is limited to 20 millifarads and the maximum frequency is 20 megahertz. But the highest measurable resistance seems to have dropped a little on this HDS160. You can see here it is 60 megohms versus the 100 megohms on the HDS120. For me, it doesn't matter that much, as the majority resistance I'm measuring is well within 10 megohms. And for higher resistance, I have dedicated meters that can measure up to 10 gigohms. And let's see what else. And you can see here the oscilloscope portion is actually identical between these two models. The bandwidth of the scope remains 1 MHz with a modest 5 megasamples per second sampling rate. Now, a few viewers did mention that they observed some excessive attenuation in the oscilloscope mode. So I guess I will need to do some testing in this video, and we will need to investigate together. Here I have the HDS120 and HDS160 side by side, and you can see that they look pretty much identical, except for the model numbers printed up here. Anyway, with the specs aside, let's actually turn it on and test out the meter. Actually, let's remove the protective film first. Alright, time to power on. Yep, the display looks exactly the same as the HDS120, and it essentially follows the same design as the OWON CMS101 clamp meter that I reviewed a while ago. And I'm sure this one also has a lighter color theme as well. So let's actually take a look. Let's go to settings, and let's go down here. I think it's tab, display, yep. You can see here, right now we're in the dark mode, and we can change it to light mode. And of course, we have to reboot the device. And yep, you can see that now we're in this lighter color theme. Now, I had changed my recording device to my phone, as the camera was just too bulky. But I noticed that on my camera, the darker theme actually showed up better on the recording, but on my phone you can see here, the lighter background actually looks better. Very interesting. All right, let's take a look at other settings. Let's move down. And it looks pretty much the same. And you can see here the HDS160 is powered by FreeRTOS, the free real-time OS. Now, I don't recall it said anything about that on the HDS120. Let's actually take a look at that. Yep, as you can see on the HDS120, it did not specifically mention the operating system type, but we do have the firmware version and also the serial number. And on the HDS160, we don't have the serial number. Very interesting. Anyway, let's move on to the DMM section here. And by the way, you can actually see here on this meter, you can set the continuity threshold. Currently is defaulted to 50 ohms. And it's actually the same on the HDS120. I actually forgot to mention that when I reviewed the other meter. So we'll definitely take a look at this shortly. And here are the supplied leads. They are exactly the same as the ones come with the HDS120, which is not surprising. And if you take a look, the tips are actually not gold-plated, which is a little bit disappointing, as some of the other meters in the same price range actually use gold-plated tips in their probes. And this meter also has the interlocking mechanism, as you can see here, just like the HDS120. The shutter would cover the input sockets if you're using the USB port, as you can see here. And of course, if you're not using the USB port, you are able to access these input jacks. So this is a safety feature, as the multimeter ground is not isolated from the rest of the circuitry. Without this shutter mechanism, you could damage the connected USB device. For example, your computer, if you happen to be doing voltage measurements while connected. Next, I'm putting the HDS160 and the 120 side by side, and we'll do some DC measurement. Now, in DC measurement range, you can actually choose between millivolts and volt measurement by pressing these two buttons. And by default, the meter is in auto-ranging mode. You can always use the up and down button to adjust manually. For example, right now, we're in the 600 volts range. And of course, to go back to auto-ranging, all you need to do is press the auto button. For our testing, we'll just use the auto-ranging, as that's probably what most people would use on a daily basis anyway. In the 60 millivolt range, this meter has a resolution of 1 microvolt. So let's actually see if we can register the change with a single count. And for testing, I'm using my MV216A voltage standard. Also, I have both meters connected to the same voltage source, so we can see the behaviors of these meters. So now let me put in 1 microvolt, 2, 3, and you can see that on the HDS160 we started registering the readings here, but on the HDS120 we haven't seen anything yet. 4, 5, 6, and you can see that we started to see the last significant digit change on the HDS120 as well. 7, 8, 9. So it seems like the minimum voltage that can be registered on the HDS120 starts around 5 microvolts, whereas on the HDS160 we can register 1 microvolt right away. 10 microvolts. And let's start with 1 millivolt at a time. 1, 2, 3. It seems that the update rates on both meters are quite comparable. 4, 5, 6, 7, 8, 9, 10. Now let me increase the voltage 10 millivolts at a time. 20, 30, and as you can see here, because the HDS120 is a 20,000 counts meter, now we actually lost 1 significant digit. So this is where you can see the benefits of a higher counts meter. On this HDS160, you can see we still have 1 microvolt resolution, whereas the HDS120, you can see now we only have 10 microvolts resolution because we're in the 200 millivolts range already. All right, let's continue increasing the voltage. 40 millivolts, 50, 60, and now of course we're exceeding 60 millivolts. That's why we also lost the last significant digit. because now we're in the 600 millivolts range on the HDS160. 70, 80, 90, 100. And as you can see that, accuracy-wise, both meters are well within their specifications. Alright, now let's test out the volt range. 1, 2, 3, and you can see that the range already changed on the HDS120 and we lost 1 digit of resolution. 4, 5, 6, 7, 8, 9, 10. And now let's take a look at the AC measurement range. And for that, I have hooked up both meters to a variac. So let me adjust the variac output voltage and let's see what is going on the meter here. And you can see that both meters are updating at roughly the same rate, but of course we have 60,000 counts, so that's why you can see that right now we're showing 1 extra digit on the HDS160, whereas the HDS120 had already changed to a higher range. So let's continue increasing the voltage. And you can see that roughly at 30 volts, both meters started warning you that you're entering the high voltage range. The update rate between these two meters are roughly the same. And the readings are roughly the same as well. So you can see that the bar graph update is very slow. That's the same issue we had with the HDS120. Now, personally, I don't find the slow updating bar graph that useful, as my primary use of the bar graph is to see the voltage fluctuation. And a faster bar graph would enable you to visualize the voltage change, even if the main display cannot catch up. Just like the HDS120, we also have this min-max display here. So how it works is, if you enable it, for the duration of this measurement, you can see that it is able to capture the min-max readings. So the implementation here is excellent, as if you want to, for example, do it again, you can press it again, and that clears out the min-max reading. So you can start afresh. All right, now let's take a look at the resistance measurement. But first, let's short out these leads. And you can see that it's relatively slow here. And we get some residual value. Let's actually press rel to zero it out. And let's try it again, as the contacts here are not that great. So let's see here, we're stable. Okay. All right, so the first resistor we're going to measure is this 100 ohm resistor. It has a 0.1% tolerance. So let's give it a go. And you can see that we're jumping a little bit. That's because, as I mentioned earlier, these leads are not gold-plated. Therefore, the resistance value at extremely low ranges are actually not that accurate. And even though we kind of zeroed it out, the residual value was actually not accurate. So let's try it again. So let me try to press it harder. And you can see that actually right now we are pretty close to the 100 ohm nominal value. And again, if I move the leads, the value jumps around, but you saw a little bit earlier, it was actually very close to 100 ohm. Yeah, as you can see here, if I apply just the right amount of pressure, the readings are actually correct. All right, now let's move on to a 1.25 kilo ohm resistor. This one is also a precision resistor with a 1% tolerance here. So first I need to get rid of the rail here, as we're measuring above 1 kilo ohm here. And you can see that we're pretty much spot on, measuring at 1.25 kilo ohm. Now, the measurement speed, as I mentioned earlier, is on the slow side for this meter. And let's try a few more resistors. This one I think is a 10 kilo ohm resistor. Let's try it out. you can see that the auto ranging is actually very slow. And let's try one more. This one, I think, is a higher value resistor. Let's give it a go. Yep, this one is a 100K. And let's try another one. This one, I think, is a 1 meg. No problem. Unfortunately, the resistance measurement mode is on the slower side compared to the other meters I have reviewed. Now let me move on to the continuity mode. So let's give it a try. And you can definitely hear that the measurement is latched, so that's not a problem. But because of the tips again, the continuity measurement is kind of a hit or miss. But that said, has nothing to do with the continuity measurement, but the tips themselves. That said, you can see here, it is actually very responsive and no problem at all. Now, one of the features I mentioned earlier is that the threshold of the continuity test can be adjusted on this meter. So let's actually take a look at that. So let's go to the settings and let's take a look here. So you can see here, by default, the sensitivity is set at 50 ohms. So let's actually change it down to, say, 9 ohms, because I have a 10 ohm resistor. The nominal value is just under 10 ohms. So in theory, if I set it to 9, it should not trigger the continuity. So let's try that. So let's see, how do we do that? And okay, I gotcha. It's actually quite intuitive. It's setting each individual digits here. So let's say we want to do 9 ohm. All right, so now it's 9 ohm. So let's go back to the continuity test. And here, let's just verify that. I'm going to go back to ohm range. So this is a 10 ohm resistor, I believe. And you can see that it's just under, well, actually right now it's above 10 ohm. So we'll see actually whether or not it triggers the continuity test. So let's go back to continuity and let's see here. And as you can see here, it does not, because it's under 10 ohms. Very good. So now let's increase it to, say, 11 ohms, and just to give it some margin, see if it triggers. So let's come here and 11, and we go back to the continuity. Yep. And you can see here, this feature worked really well. And I'm actually very happy that the meter included this feature, as you can adjust the threshold based on the current measurement requirement that you need to achieve. All right, moving on to the diode test. So let's first give a silicon diode. And you can see that we can measure the forward voltage, but there's no beep. Some meters do give you an indication that the p-n junction under test is good, but this one does not. So you can see here, we got a reading of the voltage, no problem. Now let's just move straight to a white LED here. And to see if we can display the forward voltage drop here. Yep, no problem, you can see that. We can light it up, and also the forward voltage is detected. Very good. All right, now let's move on to capacitance measurement. So for that, let's start with a small capacitor here. And let's see, I have a 22 picofarads. By the way, if you look at the display here, we do have a resolution down to 1 picofarad. So let's see if we can measure this one. Not sure if you can read, but it's 22. No, seems we can't measure it. Now, if I recall, on that HDS120, we also have similar issues. Although the minimum resolution is 1 picofarads, we were not able to measure extremely small capacitors. So let's actually increase the value a little bit. And the next one I have, let's just go straight to 68. This is a 68 picofarads capacitor. Still no. I thought on that HDS120 we were able to measure 68. Let me actually verify that. So here I have the other meter. Let's see here. And this is 68. Yeah, you can see we are able to measure that. So clearly on this HDS160, obviously the sensitivity in capacitance measurement mode had dropped compared to the HDS120. So let's come back here and see at what value we're able to register that capacitance reading. And here we have a 200 picofarads capacitor. Let's give it a try. Wow, still not able to. Okay, so let's increase to, let's say here, what is this one? This is a 33. No, it's not able to do that. This one is a 680. So let's give it a try here. And you can see that we are able to measure that 680 picofarads capacitor, although the reading is a little bit off. Now, that said, that could be because of the capacitor here. But nevertheless, the sensitivity of this HDS160 is actually quite low in terms of capacitance measurement. So that's definitely something you need to pay attention to, as if you are doing electronics, for example, very often you would need to measure capacitance of this small value. And obviously with this meter, you won't be able to do that. But with the HDS120, you are able to. So just something to keep in mind. Now let's try a 100 nanofarads capacitor, and I don't think we'll have any problem measuring it. And by the way, this one, if you remember, the nominal value is a little bit on the lower side. So let's try it here. Yeah, you can see that we got that 80 nanofarads reading with no problem. And next, let's go straight to a 15 millifarads capacitor. And it's thinking. And it's quite typical for these kind of large capacitors to take some time. And you can see that we get the 14.3 millifarads reading with no problem. So from our test, you can see that the capacitance range actually has some discrepancy between the HDS160 and the HDS120. On the HDS120, we were able to measure capacitance above 50 picofarads, whereas on the HDS160, the minimum measurable capacitance is in the hundreds of picofarads, so something to keep in mind. Now, supposedly you're able to measure frequency up to 60 MHz using the HDS160, but right now we're only able to measure up to 30 MHz with a sinusoidal input. Now, the manual did say that the frequency measurement needs to be square wave, but my signal generator can only generate square wave up to 20 MHz, so I'm using a sinusoidal input. But nevertheless, right now, the input amplitude is actually at 10 volts peak to peak. But you can see that we are only able to pick up to 30 MHz. And if I increase the frequency output, let's see, 31 MHz, it's still fine, but 32, you can see that, okay, it's still fine, 33, and no, it's not able to measure it anymore. So when you are measuring frequency using the HDS160, just want to make sure that you understand the limitations. Now let's test out the current measurement range briefly, and you just heard that it gives this beep once in a while when in current measurement. And that feature is the same as on the HDS120, and I like it a lot because that tells you that you are currently in a different measurement mode and the operator needs to pay attention. Specifically, you need to check the measurement leads are in the correct sockets. Anyway, let's give it a go. So you can see that in the current measurement, we have microamps, milliamps, and amps. So let's actually do microamp here. And you can see that in the microamp range, we have a resolution up to 10 nanoamps. So let's actually use that to measure a 100 microamp current standard. And we're getting pretty much precisely 100 microamps. And now I'm using my Unity UPD3305S, generating a 100 milliamp output. You can see that we're measuring that current with no problem. Now let me increase the current limit to 200 and 300. And you can see that because this is a 60,000 counts meter, we're actually able to measure 300 in this milliamp range. In fact, we can do that up to 600 milliamps. Let's see that, 400, 500, and now let's change to 10 milliamps at a time, 10, 20, 30, 40, and let's just go to 90, and you get the idea. And now we're in amp range. You can see that even in amp range, we have a resolution of 100 microamps. And just for completeness, I wanted to briefly mention this comp button here. The comp button here is actually useful for binning components. You can see that as soon as I press that, you see this range. The idea is that you define the range of the tolerance in the setup manual, and it will tell you if the component under measurement is inside or outside of the tolerance. I have demonstrated this feature in my HDS120 review, and you can check it out there. But if you wanted to do the setup, you can just come into the setting, and you can see here we have this comp range, and this is where you set the value. Now, in my opinion, this is probably something you would only do if you're testing a lot of components, as just to set it up can take quite a bit of time. And of course, the HDS160 also has an oscilloscope mode, but the oscilloscope mode is essentially identical to that on the HDS120, so I'm not going to go into the details here. You can see that if I press the DMM button, it will switch to the oscilloscope mode. And like I just said, the specs of the oscilloscope on this HDS160 is identical. And like the HDS120, the scope has a bandwidth of just 1 MHz with a sampling rate of 5 megasamples per second. After I reviewed the HDS120, a few people had commented that the attenuation on this scope seems to be quite significant after about 15 to 20 kHz. So let's actually investigate that to see whether or not we observe the same behavior here. For this testing, I'm using the stock leads just for the time being. As the frequency is low enough, we should be able to do that. And you can see here right now we're putting in a 1 kHz signal at 5 volts peak to peak. And the displayed value roughly matches what is the input. You can see here, let me zoom it in. So now let me increase the output frequency here. So let's do 10 kHz. And we're at 4.81. So the amplitude had dropped a little bit. Let me change the horizontal scale so that we can still see the signal here. So now it's going back to 5.0. Doesn't seem like a problem. And let's go to 15 kHz. Still 5. Let's go to 20. Still 5 volts. So I'm not observing the same problem that people had reported. And let's just keep increasing the output frequency here. So let's do 30. And you can see that roughly it still matches 40. Now the measured amplitude actually increased. This could be due to a couple of factors, because we don't have the correct termination, and obviously this causes some reflection of the signal, and that could definitely impact your amplitude reading. And also the output from the signal generator may have some variations, and also the measurement circuitry on this HDS160 may not be perfect either. So there's definitely a lot of factors can impact your reading here. Anyway, let me keep increasing the frequency here, 50, 60, and you can see that we are not seeing what other people had reported. So I'm not sure whether or not it's a quality of the signal generator or not, but it could also have something to do with the cabling. So now we're at 100 kHz. Now at frequencies above several hundred kHz, you do need to make sure that termination is correct. Otherwise the readings will be meaningless. But let's keep increasing. 200 kHz, 300, and 400, 5, 6. You can see that the measured amplitude started to drop, but this is still within the 3 dB bandwidth. 7, 8, 9, 10. So this is 1 megahertz. You can see that we're right now roughly at 3.8 volts. So that is roughly 70% of the original value. So we're still within the bandwidth limit. Also, some people were asking in the comment section in the HDS120 review video whether a 1 MHz oscilloscope is just a gimmick. Well, in my opinion, it can be very useful, especially because this is a portable device. You don't have to worry about the earth ground, and you can simply measure the mains waveform without having to worry about using a differential probe, which is typically required when using benchtop oscilloscopes. Also, the carrier frequencies of most of the VFDs are well below 1 MHz, so a handheld device like this can be useful in troubleshooting VFD devices in an industrial setting. And that's just one of the many examples. Alright, now it's time for us to do a teardown. Now, Because the specs of the HDS160 and HDS120 only differ in the multimeter section, I'm not expecting to see a huge difference inside between these two meters. But nevertheless, let's open it up and take a look. Actually, before I fully open it up, you can see that this meter is powered by a single cell, just like the HDS120, and the capacity of the battery is 2600 milliamp hours. And we have two of these fuses here. They are not HRC fuses, but just your standard fuses. As you can see here, with medium display intensity, we are drawing roughly about 50 milliamps, and this is actually quite good because we have a 2600 milliamp hour battery, and this will allow us to work continuously for at least 50 hours. So let's take a look at the oscilloscope mode. And the current draw is very similar. And right now we're in this darker theme, and you can see that with this dark theme, the current draw is actually slightly less, which is to be expected. So in this dark mode, you can increase the runtime by another 3-4%. And here is the current draw of the medium display brightness. If we increase that to high, you can see that the current draw increases significantly. But in my opinion, there's no use to use this high brightness background because the medium is actually plenty bright. And let's go back to low. And if you turn the brightness down, obviously it will improve your runtime, but this, in my opinion, is too low. So the default medium is actually the sweet spot. Well, here's something for a change. This time I can actually see the markings on this multimeter chip, and it has not been removed. So let's actually take a look at what chip they're using here. And let's see if we can zoom in. And you can see the chip number is HY3131. This is actually more interesting because if you look at the datasheet here, you can see that the HY3131 is actually meant for a 50,000 counts multimeter, but here we have a 60,000 counts multimeter. So I'm not sure how OWON managed to squeeze out the 60,000 counts from a 50,000 counts chip. My guess is that from a digitization perspective, the chip is probably capable of digitizing 60,000 counts. Perhaps the accuracy and linearity is not guaranteed in that range. So I'm not exactly sure. Nevertheless, this is a 60,000 counts meter, and OWON somehow managed to achieve that. And it looks like the user interface and the oscilloscope is implemented using this HC32F460 microcontroller up here. And this is actually the same ARM Cortex-M4 microcontroller used in the HDS120. I guess that's not surprising, but you can see here compared to the HDS120, the board layout changed ever so slightly in this section here, and that is probably to accommodate the new DMM chip. And the DMM section design is also ever so slightly different. You can see that on this HDS160, we actually don't have the isolation cutouts around the fuses. I'm not sure why that's the case, but those cutouts are with the HDS120 design. Other than that, I think the overall board layout and the design here is quite solid. Overall, just like the HDS120, the HDS160 is pretty well designed and pretty well built. For just $10 more, you can have a 60,000 counts multimeter while not compromising a lot of other things. Now, the only gripe I had is that the capacitance range, the measurement somehow did not have the same sensitivity as the HDS120. So that could be a deal breaker if you mainly need to measure small capacitance. But as I have demonstrated, everything else between these two meters are pretty much identical. Now, there are some minor tweaks in the firmware in the HDS160, but nothing more beyond that. So unless you are on a tight budget, you probably wanted to go with the HDS160. But to be quite honest, either meter probably would just be fine for most of the users. Well, I hope you enjoyed this review and teardown. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to this channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.